right, Engine Performance Expo viewers, you know, this is one of my favorite guys, and this is one of my favorite topics. I mean, Dan, you got hydrodynamic lubrication going on in the background. How cool is that?
It's so cool. I don't think there's a much better topic personally myself.
Well, I mean, you're a bearing guy, you know, I'm an oil guy, exactly. So hey, it's like peanut butter and jelly right now.
That's right.
So explain to everybody, what are we actually seeing here in the background?
Well, to start out with, I always want to explain what a bearing does. So we have a moving shaft that's running around here, and now the brown would be the oil. So you have a wedge, and as this crankshaft is spinning, it's self-renewing itself
drawing the oil into that.
Yeah. I always think...
It's called viscosity, by the way. Viscosity is a fancy word for resistance to flow, so that rotation of the journal is what's dragging it through the viscosity, dragging it in, and it's creating this...
pressure. So we have pressure coming down as the engine fires. All right, but that's not always going to be the case. We're going to talk about that. It's not, pressure doesn't always mean it's firing down. Sometimes it can go opposite directions. More to come on that. Wedge, simple thing. I always look at it, it's like, if I want to keep the door open, I stick a wedge underneath the door. The harder I push, the further
it pushes up the door, lock the door in place.
So that's what we got right here, is just so everybody understands.
Trying to keep the crankshaft off the bearing.
Off the bearing. That's the whole point there.
Okay.
So.
All right, so that's oil wedge, right? So how we begin to apply this to bearing design, and the point of this whole session is about identifying bearing failures, because this one is everything is in hunky-dory shape.
This is good.
This is
happy,
good.
Happy space, man.
Yeah. But what about the bad ones? Let's take a look at some of the bad ones and talk through how we know what's gone wrong.
Absolutely, because we see those from time to time. All right, so I did a little study, and as Clevite, we have analyzed a lot of bearings, and not necessarily failures, but things that happen. 50%, 45% of bearings that we get reported are from dirt.
That's the problem, right? There's some kind of
dirt. Now I say dirt.
Damage or something. It's some kind of debris.
Some kind of debris. We say dirt. It could be numerous things, honing stones, dirt floating around. Yeah. You know, whatever. Your lunch.
Yeah. There are things that get in engines that shouldn't get in engines.
Exactly.
You know? Yeah.
So then we have a list of everything: misalignment, lubrication, overloading, corrosion.
Yeah.
There's a bunch of 45% of bearings, dirt.
Well, I also happen to know the guys at Timken who make rolling element bearings predominantly. It's the #1 source of bearing failure for them is contamination. It's dirt, something like that. That's the #1. And guess what? And then it is misassembly is #2. So guess what? I guess rolling element bearings and plain bearings, they suffer from the same mode of failure.
Exactly. There's a common theme here.
Don't get them dirty, by the way.
Nope.
You know. So
very cool. So before we get into what's wrong, let's talk about what's right.
Oh, that's great. Yeah.
Okay. So typically a bearing, you will have a wear in this being an upper bearing, rod bearing, and it will have a wear on about 2/3 of it.
Okay.
Just kind of a nice universal. The area circled here, there's eccentricity, which creates that wedge.
That's the relief area.
Yep. That's the wedge part. And then the very end, there's bore relief. So that covers if there's cap shift, if there's deformation, if they're in a connecting rod, because as it fires, the load goes...
It lets it have
oval
area for compensation.
Absolutely, because if you scub off here, you've closed that wedge up.
Got it.
When you close the wedge, you lost your oil film.
And bad things happen.
That goes to #2 where you lost oil.
Yeah, you don't want that.
Don't want that.
All right, so now we know what normal looks like. All right, we're now going to start looking at some of the things that are abnormal, where there's debris that's causing that damage, and how do you know that's debris by looking at it?
Right. So typically a debris, in this particular case, we have a bearing, there's a piece of debris that's up here, and the debris, all bearings have embeddability.
Yep.
All right, so the harder the bearing, the less embeddability it has. The softer the bearing, the more embeddability it has. Pretty simple, right?
Yep.
But on the flip side, you have to be careful, because too soft a bearing allows it to move too much, and you can create other issues. But for simplicity, if a piece of foreign material, and here this looks like it's some kind of a cleaning chip or something. Who knows? Yeah. We don't know really for sure. Higher microscopic view, but basically it gets in and a bearing has embeddability.
Yeah.
So embeddability in the overlay embeddability in the substrate.
Okay.
So it keeps something in there. And when that gets in there, you're disrupting the oil flow.
Yeah, right, exactly.
Back to that again. It's all about the oil.
See, I told you I love this guy. I love these conversations because it is the oil and the bearings, they work together. That hydrodynamic oil wedge,
Yes.
anything that disturbs it, it's like a boulder that creates a rapid.
Exactly.
Right? So it's not smoothly flowing anymore. We've got turbulence, and that's not good.
Yeah, exactly. Very true.
What's neat about this, too, is you're kind of showing that it actually had debris on the back side of the bearing and on the inside, because the debris doesn't always have to necessarily be on the running surface of the bearing to cause a problem. It can be on the back side as well.
Yeah, backside, usually when you see the backside is the when assembler is doing it and you have dirty environment that the bearings put into.
So keep the bead blast on the other side of the shop from the assembly room.
Or in this case, on back of the bearing, nice aluminum chip right there.
Yeah.
Now, we know there's aluminum chips in the shop.
It happens.
All right.
Yeah.
So what happens is the aluminum chip gets in the back, the bearings put together, and now you've disrupted the oil film. The place.
The wedge is now lost because you've disrupted it. It's like a ski jump in there.
So
it shouldn't be.
It pushes harder on the overlay because you have bent the bearing.
Right.
And now you're getting a contact on that particular point. And so if you can get a contact, which we're fortunate on this one, where you actually can see the debris still wedged in there.
Well, you're also taking up clearance too. So you change the clearance. So now, because those oil films get very, very thin under very high pressure, well, now we have an obstacle, if you will, that can actually even shorten that clearance up even more. So it's going to have contact that's going to begin to wear prematurely because it's non-uniform in distribution.
And also in doing that, you're creating a frictional temperature.
Oh, yes.
So we're going to get into frictional temperatures again, but anytime you get some kind of debris that's pushing something in there, you can get some frictional temperatures. So typical contamination. Now this is this came out of one engine.
Okay.
Right. So the complaint was the engine failed.
Yep.
All right. As I looked into this a little bit more, contamination on the main bearing.
Yep, you can see that.
And what I did is I looked at these, and these are rod bearings off that engine, and I have different rod bearings. So this is the steps of progression of a bearing would go bad. All right, so here we have some, you can notice that there's some overlay. You can see the gray with the copper. All right, so yeah, it's going bad. That's pretty bad. Well, now we go to the next bearing, and there is no gray. There's no overlay at all.
Right.
It's gone. You're getting a lot of surface temperature because of losing oil. Clearance got bigger. Right. And you're actually getting burnt oil embedded in.
Now that overlay, just for future, because we're going to talk about it later, the material is going to be tin and lead, correct?
Tin and lead. Copper tin lead is typical of a street bearing.
Okay.
Yes. Yeah. Yes. And then unless you get into a really high performance, then it's a lead indium.
Right. Yeah.
But for today, we're going to go with the copper tin lead overlay. So some on there, it's gone.
Yep.
All right. Here it's really gone. Now we've completely lost the substrate.
Yeah, it's totally wiped out. Yeah.
The bearing spun, you can see by the outside, the bearing spun around.
Yep.
Simply the fact that it lost so much oil clearance, the frictional temperature got hot.
Yep.
The bearing said, I'm grabbing onto you and I'm going around.
Yeah.
And
she's done.
That's it.
Yeah.
Yep, bad day.
Yeah.
So I take those two bearings right there and we'll go to same bearings.
Yep.
Right? But you notice as you stack them up, you can see that they're lined up here.
Yep.
But you can see as the bearing gets hot, they close in on themselves.
You can see the creep.
Absolutely.
That temperature causing it to creep in.
And so as the bearing...
No wonder it spins, right? It creeps in and loses all of its crush.
Loses all the crush. And we just talked about the oil film.
Yeah.
So you've closed in. Now you've brought that bearing together.
Yep.
There's no space for it to get an oil.
Yeah, no more oil wedge.
So
everything's bad.
That's how you progress from this to that. You get temperature in it, as you can see, to the other bearing where it started to spin. The next thing what's going to happen here is this bearing was going to go round and round with the crankshaft.
Oh yeah, it's about to go for a ride. Yeah.
Another bad day.
Yeah, really bad days.
So,
oh yeah. Yeah. So and this is an aluminum, so it's a bimetal, so not copper, tin, and lead.
That is correct.
This is different. This is going to be aluminum. Now, what's the overlay on aluminum?
Aluminum. It's a steel backing.
Okay.
It's a foil with a substrate with another foil, and it's centered together.
Okay.
It's basically heated and squeezed together to become a
thin layers of aluminum, essentially.
That is correct.
Okay.
Yep.
All right.
And this one, as you can see, again, debris.
Yep.
You can see the discoloration. Anytime you see black, it's heat.
Yeah, exactly. Yeah,
it's heat.
That's burnt oil.
That's burnt oil,
burnt oil
sticking to
yeah,
it. Exactly.
Yeah.
So what, based off the previous slide, the next thing that's going to happen is you get enough oil in here, you're not getting oil, bearing's going to get hot, close, it's going to spin.
Yep.
Same thing's going to happen.
All right, that's the mode of failure. Now, this is an interesting one. So in this case, we have the locating lug, right, which a lot of people kind of mistake. The lug isn't what makes tension. It's just to make sure it's aligned properly.
Locating lug means it's just to locate. Okay, as we design bearings, nowhere is the locating lug used to support the bearing to keep it from spinning. It is strictly locating. Matter of fact, some bearings don't even have locating lugs on there. So
we've seen those, and it freaks people out, by the way. They go, ah!
It's okay.
Where do I go? I don't know where to put it.
Now, there's other issues that can happen with that, but but the locating lug is simply just to put it in its right nesting
it
spot.
Locates it. Yeah.
Exactly.
The name's it. So it needs to go where it's supposed to go, not where it doesn't.
Exactly. So in some cases, I don't know what this. He probably has an upper and a lower mixed up.
Right. Yeah.
And it doesn't fit. And again, if you would put this together, it's going to squeeze together, lose the oil film. And
right. I would think you would feel it beforehand, but you never can tell.
This is true. Remember, that was on one of the topics.
Yeah, exactly. All right. Oh, so this is someone we've seen before.
Yeah. Yes.
That the oil holes can get blocked or not aligned properly, and that's a huge issue because there's no oil supply, there's no oil film.
Right. There's two examples right here. Now this one here. Obviously, what he's doing is he's putting the upper and the lower and the lower and the upper.
Right.
All right. There's no oil hole. Right. This one was closer to successful, but there was the bearing was not in the right location, and when you put it together, it just closed the hole out.
Yeah.
Right. It fit and it rotated. You wouldn't know, other than need to make sure that the oil hole has a feed hole.
Now, I would think, I'm speculating here on the fly, that in this case, you would see extremely high oil pressure if you were running in the engine, because you're not going to get a lot of oil flow from that point, I would think, but maybe I'm wrong.
I don't think you would see as much based off of how many rod journals it's feeding.
Okay, maybe that's true, right?
Okay, because if you're front rear and you're only feeding up one, it's a lot less. So you
may not jump out as obviously.
It may be a little.
Well, you get all of them that way, maybe so.
Maybe so.
But if only one of them's wrong,
you may not notice it.
But it'll still throw a hole to the side of the oil pan.
Yeah, you will notice it eventually.
Yes, you will eventually find out. Okay, so we know that if you have the oil holes misaligned, then it won't flow oil. And oil starvation is a really bad thing, which, hey, the next slide is all about oil starvation.
Exactly. So typically, oil film thickness is about 2/10. So, all right, you set your clearance, say 2,000s, you got 2,000s. Well, that is quantity to fill in to 2/10. Now,
it's going to taper down to
2/10 is your oil film thickness.
That's not much.
That's not much. So now we're going to put it under load, and we could get that down to 1/10.
A tenth.
A tenth.
Wow.
Yes. So.
Sorry, Mr. Bianchi.
No problem. You're good.
Want to restart?
Not sure where he was in that. Yeah, let's act like we're starting over again.
Let's start with this slide all over.
Yeah. So when you're editing, pick up back at this point. When I'm pointing like this, that's the spot. Okay. Okay, so when you get the oil holes misaligned, that basically cuts off the oil to the bearing, so it's oil starvation, which, guess what? The next slide is oil starvation.
Exactly. When you set bearing clearance, you just set a couple thou clearance, plus or minus, based off shaft size, and we get all that. When you get that much clearance, the wedge of it, 2,000s, let's say, will actually come down to 2/10 of oil film thickness between the journal and the bearing.
From 2 thou to 2/10. Yeah, that's not much.
That's not much. And then, let's put that engine under a heavy load.
Yeah.
Now we're down to 1/10. So there's not a lot of margin here in what we're playing with. So it's very important that we get the oil to where it needs to be and maintain that oil film thickness so we don't get bearing contact with the shaft to create frictional temperature.
Well, because once it happens, it's basically
It goes
game over.
downhill.
Yeah, real quickly.
Exactly.
Yeah, so that
Yes.
that 1/10
1/10.
is your shield. That's it. It's
That's it.
very strong, but very thin, so you got to maintain it with all the protection you possibly can, which is why alignment and cleanliness and all that is so important, because you have a very, very small 1/10 of a thou margin of error, apparently.
I can't see 1/10. That's pretty small.
That's 100 micro inches. That's what that is. So now this brings up the next point.
All right, so what I have here, just kind of, it's a picture, it's an FEA picture of a crankshaft.
Yep.
We have a main bearing 1
Yep.
on the left and main bearing 2. So as we're going to talk about this shaft, the shafts don't always stay straight. As they fire, a crankshaft will bend and things happen to it. So the simulation here, main bearing 1, main bearing 2, you can see that the crankshaft is bending. So what our 2000s clearance, if we're going to use that number, our 2000 clearance now has a tilt. So it starts getting bigger.
Right.
So now your 2000s of clearance it got much less. And that in turn is affecting your film pressure, which allows journal to bearing contact. Okay. So perfect case scenario, this is a picture of a crank. This is a happy crank.
Happy crank, right?
Happy crank.
Okay.
All right, there's space. All right. Pressure, as the engine fires, pressure's coming down, so you know this is going to be where your minimum oil film thicknesses are
right
at.
down here. Yeah.
Right,
makes sense where it is in terms of rotation. Yeah.
Right. All right, so this would be the highest pressure and the lowest film thickness.
Right.
Okay, so as that crank bends, now you can move it to where it's orbiting.
Yeah.
Okay, so you notice there's no places for it to fill oil into the wedge, because they're all void because of how close it's running, because the crank now all of a sudden in simulation grew.
Essentially, yeah. It's like turning off the valve. You're not letting enough oil flow across the face of the bearing anymore, because there's not enough running clearance anymore.
Exactly.
Because the flexing is taking up the clearance.
So as you're running, all of a sudden if you take an engine apart and you look at it, it's like the engine's firing, and remember we just talked about the force goes down, right?
Right.
Not always. If you have a crank bend, you can see how low the oil film thickness is up here because of crank deflection, and you're going to get bearing wear here. You can get a spot here. You can get a spot here.
Well, that was the big deal in the restrictor plate motors.
Yes.
That where the main bearing wear wasn't on the lowers, it was on the uppers. Actually, my bad. It was on the lowers where it was the piston rod is trying to go out the cylinder head.
Absolutely.
The exhaust valve opens, and there's so little cylinder pressure that piston's going up so fast, it's trying to just yank it out, and then it was actually just killing that lower.
Well, I still have customers that have heavy mass rotating, and every time the exhaust stroke, it's trying to throw the piston out the exhaust port.
Yeah.
And they're getting cap wear.
And that's what you're seeing.
That's exactly what you're seeing. And you're going to see, now we're going to talk about crank load and the load on that connecting rod bearing.
All right. Oh, yeah.
So this is a typical LS bearing. I love this picture because there's so much happening in here. Same engine, number 2 and number 4.
Okay.
But you notice how this part of the bearing looks very good, and there's an angle. This is an upper. Notice most have grooves. So in this case, we have the crank bending up.
Right.
So you're getting fatiguing. You're getting deflection at an angle on the upper.
Because this is where that clearance is being taken up by the bending of the crankshaft. The dynamic motion of the crankshaft is taking up that running clearance and compromising the oil film locally.
Yes. Same bearing, same engine, number 4. Same thing. You can see there's different deflection going on in the crankshaft, but you can see how it's wearing on half of it, but not the other half. So a lot of people say, "Well, it can't be because my bearing looks good on this side."
Right.
Well, you're taking the fact that the crank is staying straight, and we know that's not the case.
Right.
This is showing because of where it's at, and again, this one's actually at an angle where it's loading.
And this is really important to understand for choosing bearing clearance. Actually,
very true.
This would be a limit of how tight you can run your bearing clearance is how stiff or much motion there is in your crankshaft. The more your crankshaft moves, the more clearance you're going to have to give it to allow for that deflection.
Until you run out of oil flow.
Right.
Yeah. But in this case, in this case, you can see the bearing is wearing here to this case. There's so much wear on this bearing that the copper is showing again uppers. These are uppers.
Yeah.
All right. There's a higher view of it right here where the crankshaft is hitting so hard here in the fatigue that the copper is showing in here. But as you can see in the other areas, the bearings still look relatively good.
Yeah, it's just in that area is where that flex is, and it's just killing the oil film there.
Yes.
Locally.
Yep. In an upper.
Yep.
Okay, so an interesting thing, I had the opportunity years ago to do some testing. So I took this crankshaft.
Yep.
And if you look real close, there's some instrumentation on there.
Yep.
Where I've actually have pressure sensors in the crankshaft as it's running. This is the wires as it's coming in there. And we measured the pressure at a main and the rod. So a lot of people are saying, oh, make more power. How you make more power? You get rid of parasitic
loss,
oil pressure.
Yep.
We reduce oil pressure, we're going to make more power, right?
Oh, yeah.
So
zero oil pressure at Daytona. Remember those days?
Yeah, yes, I do.
Don't mind that gauge. It doesn't matter.
So what I did, we ran a test, and blue, red, white. This is galley pressure. So people are looking at, I got 60 pounds or 55 pounds of oil pressure.
In the main gallery.
In the main gallery.
Yep.
Not what the crank sees.
Yeah.
All right, so this is where the crankshaft is at on the main. This is the rods. So as we go through here, the rod pressure is dropping significantly from what the galley pressure was. At 8,500, we lost 36 psi.
Wow.
If it started out at 55.
Yeah.
At 9,000, we lost 44 psi at the rod journal. We were basically running at 11 psi. So my worry is if you're thinking, oh, I'm going to reduce oil flow and make more power, keep that rod bearing in mind if you're running less oil pressure at a high RPM, because you can get to a point where you start the bearing out of oil.
Ooh, yeah. I think we've all seen that happen before, by the way. Yeah, and this is, again, oil starvation, where it's just not enough oil getting there.
Yep. Yeah, and you can tell this bearing is getting hot, and if you look, you can actually see on the bore relief, as I talked about, it's actually moving metal.
Yeah, it's always
moving over.
It
is smearing it over. Next thing's going to happen, it's going to get black, get down to the substrate, close, spin, rod out the side.
Again. Yeah.
So again, oil starvation, another prime example.
Being material transfer.
Moving material transfer, it's just smearing it over.
Because that's really, if you see anything in that relief area, that's a big red flag. That's a giant problem.
Yeah, there should never be. So typically, in this area here, by a 1/4 inch, plus or minus, depending on the bearing design, there should be 0.5 to a thou more clearance than at this.
So that's with that much more clearance, nothing should be in there.
Nothing should be in there. If it is, it's a great place for it to capture what's in there, but it's going to go bad from there.
Yeah.
So corrosion.
Oh, yeah. Well, it says right here, fuel, right? Fuel is the enemy of your oil. I mean, I talked about it before. The same base oil that's used to make engine oil is also used to make turbine engine oil. And an oil that may last, say, 3,000, even 5,000 miles in a passenger car can literally last 30 years in a turbine. What's the difference? Turbines are not exposed to it, right? I mean, the piston ring guy's like, hey, we live because there's combustion up here, and it's the contamination of the unburnt fuel in the blow-by that kills the oil. So it's the acids that are created from the fuel itself and from the moisture, right? The combination in the old days, especially with diesels, there was a test that was really common in used oil analysis called TBN, total base number. And where that derived from was testing for corrosion wear, essentially. Because what happened in a diesel is those heavy diesel fuels in the old days were high sulfur.
Yes.
Well, then you're making water with combustion. Well, water and sulfur together make sulfuric acid. So what would eat your engine alive was the sulfuric acid. So they created detergent additives that had this overbase to them that could neutralize the strong acids. So what TBN as a test is taking hydrochloric acid, another strong acid, and it's neutralizing the oil to see how much alkalinity is left in the oil to neutralize those strong acids. So yes, this is a big thing where when you don't change your oil properly, and if you have a bad tune-up and you're putting a bunch of crap in your oil, this is what's going to happen.
Yes. So
the hot short.
The hot short. So first time I saw this, we were at Pocono in a NASCAR race.
Yeah.
Had a red flag. And in typical NASCAR fashion, everybody parks at the bank, right?
Yep.
All right, green, white checker, 5 laps to go. The car took off, finished the race, 5 laps. All right, so we get the engine back. I look at the bearings, and there's chunks missing out of it.
Gone.
Yeah, gone. I'm like, we finished the race. Right? How did that happen?
Yeah.
How did it happen? So a hot short, if an engine runs really hot and it's immediately shut off, it will heat soak.
The temperatures actually increase momentarily.
Yes.
So all the cooling's been shut off, but the radiant heat is there. So the latency of that heat without the cooling effect actually makes the localized temperatures go up momentarily.
Exactly. So a typical copper tin lead overlay we talked about is marked up there. 449 degrees tin melts at.
Ooh, okay.
629 degrees lead marks at. So if that heat soaks and you start melting out the element of tin or lead and you start it back up, it will actually just take that all that material and go whoosh, and you end up with a bearing that has some copper on there and the overlay is just completely wiped off. In some cases it's flaking and still hanging on there. Demolition derby cars, I saw some of this happen.
Okay,
where
that totally makes sense, yeah.
They're running and they stop and engine shuts off. Well, they're already blowing water out. You're running.
Cranks, you run it again.
Dirt late model races, and they're running real hard, and they hit the wall, and the engine immediately shuts off, and it's already a higher temperature, and the heat soak can actually melt the overlay on the bearing, and then when you first start up, it adheres to the crank, and it will spin it off.
Interesting. It's like micro welding for bearings.
It is.
Yeah. So, bent connecting rod.
Bent connecting rod. Bent connecting rod is when the connecting rod's bent, and you can usually see it's more of an elliptical wear pattern where as it's coming down, it's loading this way.
Could be similar to the crankshaft flex, but not the same.
Correct, and specifically connecting rod crankshaft flex is going to show up on a main bearing.
Mains, and this will show up on the rods.
That is correct. Yes.
Okay. Can you ever see any crankshaft flex show up on the connecting rods?
No, typically the crankshaft flex is from the rod journal to the main journal, and it's flexing. Flexing this way.
All right. Yeah.
So that stays pretty well round. Now there is some ovality that happens in high RPMs, high frequencies where it's drilled too much, but we're not going to go there.
Got it. Twist connecting rod. Yeah, you can kind of see it right there.
because it's running at an angle.
Yeah, because it's not straight anymore.
Exactly. So.
Oh yeah, here it's more edge loading.
Edge loading. So as these engines run, you come back in and your rod journal, you can get taper, hourglass, or barrel. So
for repolishing, reworking the crank.
Yeah. Polishing is no sparks.
Okay.
Typically speaking, if you're sparking, you're beyond polishing.
That's grinding.
Grinding, and you can get some taper. So checking a mic and checking because what clearance are you really setting it to?
Yeah.
If it's taper like this here. So taper, you're going to have tighter spots and looser spots. So it's going to show an area where it's based on where the shape of the journal would actually be.
So the geometry of the journal really can influence this as well.
Yeah. So in a perfect world, every engine bearing is designed. It is a round bore with a round shaft. Now in the real world, when we come in here, it may not be round.
Right.
So all you're doing is showing that issue in a higher level.
Got it.
All right, so
yeah.
main bore alignment.
Yeah.
You know, if you said
That's kind of fundamentals right there, right? It's like the house, if the foundation is not level, don't even try to build the house.
Try to do it,
yeah,
right?
Exactly,
you know, it's important, but you know, to this day we still see it. All the main bearings may not be in a line, so your clearance and your space to get oil in there is changes from journal to journal,
right?
And you end up with contact in different cases, you know, where you're actually seeing substrate come through.
Yeah,
doing that. So. All right, simple way, you know, don't forget to check crankshaft.
Yep.
Is it straight?
Make sure
put an
it's not
indicator
bent.
on there. Yep.
Yeah.
Fillet Ride.
Yeah.
This has become more and more of a common thing that we're seeing as engines are making more power.
Right.
We're getting crankshaft designers are to increase strength because, as I mentioned, the shaft will bend from the journal to the mains.
Right.
So to increase a fillet, which the fillet is the difference between the journal and the transition to the cheek, would be the radius of it. So to put more mass material there will strengthen that to take some of the flex out of it.
Okay, so that makes sense. Like with the Engine Performance Expo engine, boosted, hey, we know we like more boost, it makes more power,
Sure.
it's fun.
Sure, oh, it's
but
fun.
you need a stronger crankshaft. So the way the crankshaft designers are trying to increase that strength for more boost is adding more meat to that fillet radius,
Yep.
but now it's taking up that clearance between the edge of the bearing.
You're right, exactly. So it's going point load at the corner of the bearings, and you can see it on the
see
bearings
those
where
marks right
is that
there.
getting copper showing on there. And usually when that happens, you're going to see it all the ways around. Okay, because as the bearing's going around, you're seeing it all the ways around the bearing, and it's showing copper. Now, in some cases, it'll wear in. You can actually, if it's bad enough, when I worked in the NASCAR shops, I was in charge of NDT, and you actually can get a point where you put a stress point into the fillet. Stress point of a fillet, that's the first place it will want to crack.
Yeah, that's no good.
That's no good. So you're inducing
a failure
mode into that by that. Also, if you, on a main, if you have it right up on the fillet, the crank can feel spongy.
Okay.
So you're typically not going to have your thrust set correctly because it's not going up against the thrust surface because it's a.
So you can kind of feel that when you're checking your thrust, right? It won't feel, it said, more a little spongy as opposed to solid
because it's riding up on the radiuses.
Okay. A little assembly tip there for you.
There you go.
If you feel that sponginess, it's not like a click, click. It's a then maybe there's a problem.
The clunk is good.
Clunk is good in this case. Usually clunks are not good. In this case, clunks are your friend. Okay.
So, overlay fatigue.
This is the best section, by the way.
So overlay fatigue is when there's so much stresses going on the bearing, crankshaft moving, loads, whatever's happening, where the overlay is moving around.
It begins to crack.
It begins to crack. And it looks like that spider webbing going on there, which is showing around, different levels. And in this case, it looks really bad.
Yeah.
But it's really not as bad as it looks because the bearing's designed to absorb some of that and fatigue. Now, once you start losing pieces of it, it gets really bad.
Right.
The interesting thing, this set right here, if you look...
Ooh, yeah, there's two things going on here.
Yes, sir. You look, all right, a lot of fatigue going on here, but if you look at how these are elliptical
Very
shaped...
concentrated right here.
And it's clear in the middle. On the ends. Crankshaft flex.
Yeah.
So you're fatiguing in a part of the bearing, but not the whole bearing.
Yep.
All right. Typically, when you see something like this, that could be a connecting rod bearing where it's just that amount of cylinder pressure firing in there, moving it. This is crank flex moving around, and you're seeing it wearing. Ironically, it's a lot of flex going on here. You're getting front, rear.
Yep. And you can see it. You can see those areas where it's moving, just like you said. That's really clear.
That's crank flex going on, causing fatigue. Not to the point of some of the other ones we had where we were seeing it polishing through and getting into bronze and so forth like that.
But the real key here is that this is the overlay cracking because the underlay is moving.
That is correct. Absolutely.
Because of the amount of load, right?
The amount of load. So typically, when the underlay is moving, is you're going to see it more on a centered bearing than a cast bearing.
Right. Now explain why. What the difference between a centered and a cast bearing is.
Okay, so the substrate is copper, tin, and lead.
Right.
All right, so a centered bearing, you take copper, tin, lead, you mix it together, and it's 3 elements.
Yep.
All right. In a cast bearing, you take copper, tin, and lead, and you melt it together. And when copper, tin becomes one by melting it together and fusing it and crystallizing, it grows crystals, it becomes an alloy.
Bronze.
Bronze.
Yep.
Exactly.
The good old Bronze Age. Yep.
Yeah, there we go. So the lead helps is as it creates crystals, bronze crystals, the lead helps soften those to give it some movement, and also is, far as we talked about earlier, foreign debris. It allows it to trap embeddability is what we call that.
So the grain structure is changing, giving it strength and some embeddability at the same time.
Right, because you can't create grain structure unless you change it from an element to an alloy.
Right, you got to melt it. Yeah,
you have to melt it, so you get better adhesion. You don't get the cracks that you do with sintering, and that's why typically a cast bearing is 20 to 30% stronger to prevent fatiguing, because it becomes an alloy of bronze with lead that softens it.
That's
so
cool.
all our H and V bearings use a cast, which we own that facility, and that's where it comes from.
Cool. All right, here we go. Oh, and there's the witness mark. Right?
There it is.
So when it cracks, because it was moving underneath, it's beginning to break underneath, and now the pothole.
It just pulls a chunk out of it.
Yep.
So, basically that's a fatigue thing that's going on there. So surface fatigue, if you look at the bearing, and you have cracks in a sintered bearing that will connect the lead, will connect the cracks, will connect through the lead to a point that it will just pop a piece off. So if you ever take an engine apart, it's a sintered bearing, and you're looking, it's like, why am I missing a chunk of the bearing?
Yeah,
that's right. It may not be anything that you did wrong. It's simply the fact of the load allowed the cracks to connect to the point that a piece came out. Now that can be a different level. Yeah. So
watch this. Don't tune away, because this is the best part.
I love this. This is so much fun. This is one of those late night dreams that I had about doing this. So I got up and I asked my kids to make me some Jell-O.
Okay.
Of course, they didn't know why, but I'm going to use the Jell-O. A steel bowl would be the steel backing of the bearing.
Exactly. Yep.
All right. So then I said I wanted some orange Jell-O.
Yeah. Copper.
You got it.
Yeah.
You got it. So the copper, so that would be represent our substrate.
Yep.
So now that's the base part of the. So then at that point, I needed to plate it.
There goes your overlay. There you go.
It's pretty hard to electroplate
Jell-O. Yeah.
So what I did is a good old can of Rust-Oleum.
There you go. Good plan.
Pretty lousy paint job, I admit, but get your point. So I have an overlay. Bearing looks good. Comes out of the box. Looks great, right?
Yeah, looks fantastic.
Put it in the engine, and torsionals happen. Everything happens, and you end up with that fatiguing. Basically, what happened is your Jell-O shook.
Yeah. The overlay's cracking because the Jell-O's moving.
Exactly. So once the Jell-O starts moving, you get these fatigue lines in your overlay is exactly what you're seeing on the fatigue.
Got it.
So like building a house. You don't build it with 2x2 walls. You build it with 2x4, 2x6, something stronger to support the roof.
Right.
Because when it starts moving, the roof shakes and you get fatiguing.
Right. And you don't want your house falling apart.
Don't make it out of Jell-O.
No. Good old bearing crush.
Bearing crush. So as we mentioned earlier, locating tanks.
Or for locating.
They're
not creating.
Not crush.
Yeah.
So when we design a bearing, we take the housing bore and we know what the housing bore is, what we recommend that housing bore to be.
Right.
And typically a bearing will have, on a shell, will have about 5 thousandths, give or take how big the shaft, or how big the housing bore is.
Right.
It will have about 5 thousandths of standoff times 2, 10 thousandths, and it will create what we call radial pressure, and it will force that bearing to stick with the And then as it's staying where it's supposed to be, you're gonna have to scoot back. Yeah. So
there you go.
So as it's saying, is the radial pressure holds the bearing in place.
Yeah.
So the one thing that we have found is on typical applications, if a guy takes steel connecting rods and he puts aluminum in, right, there's more thermal growth. So
yes, the aluminum is going to grow. The housing board is going to get larger during operation.
Absolutely.
So it's going to lose some crush.
It's going to lose crush. So at that point, you can have a bearing that loses the radial pressure and the bearing starts to spin.
Right.
All right. So if you, on the flip side, if you have, I hate when people change housing bores to fit oil clearance, all right, because you're affecting the crush,
right?
All right, so they tighten it up, reduce oil clearance. All right, on the same token, they can open it up and
open up clearance, but you're reducing crush.
Reduce the crush, so then you get where the bearing is walking around and causing on the back where it's fatiguing.
A little fretting and all that.
Typically, you can get it on the connecting rods as well, where on the point loads, where it will start to fatigue and fracture and fret the connecting rod. So you actually can decrease your life of the rod because you're creating stress points again
because you're putting too much crush into it, and
it's moving.
Yeah.
So
well, one thing about this too makes me think about the Engine Performance Expo engine being an aluminum rod engine. We came to you and you're like, here, you need to run this bearing, not that bearing, so you have the proper amount of crush so that the standoff would change for that aluminum rod.
Exactly.
Yeah.
Exactly, for that reason. So,
and if you get too much,
the bearing, you can't get enough stress on the hoop stress. So at that point, the bearing is buckling. So in this case, you can see it's buckled in this area right here.
And that's distorting the oil wedge, so that kills your oil film.
Yep.
And then the other thing here is, the dowel.
Dowel. So it's a small cross-section area.
Yes, it buckles
up.
So
it makes it real easy to say, I give up right here.
Right, yeah. There's the high spot. I'm going to show you where the high spot is.
Exactly. So back to the fretting now.
Yep.
So as the bearings move around, typically you'll see fretting on the back side of the bearing. And that's because the bearing is sitting there moving around as firing pressures come in and the bores are changing the size and dimensions. The bearing is trying to move with it. Yep. And if they're not moving in harmony, you get this fretting that goes on there.
It's a big issue also in rolling element bearings. Fretting is an issue. Rolling element or plain bearing, it's still an issue.
Moving components need to move in harmony.
Right,
When they don't. So connecting rod bearing loads. All right, so as we mentioned, loads. So 720 degrees of rotation, you will see that, notice that
those loads change
the loads
dramatically
change
based on where they are in the cycle.
Right.
Yeah.
But the other thing, your load, as you would expect, it creates more of an oval.
Right.
So
a circle is
so as your housing bore in a connecting rod, your housing bore will follow that shape.
Okay.
So your housing bore can actually open and close. So if you upgrade power, you up power adders, bigger, nicer cylinder heads, camshaft, whatever it might be, you can change this and you didn't upgrade your rods, you can change that to the point where you can pinch off oil flow and, again, lose the oil film. So by not having a sturdy, strong enough rod to withstand the movement of the connecting rod.
You can see that in the plate engines too. They got everything so light. Now the rod was like spaghetti, and it's like
Yep, absolutely. So oil breakdown. This is right in your alley here.
Which is kind of neat because you're seeing is a spectrograph of the different elements from the oil itself. So we were talking earlier about calcium. Being that detergent additive, that's the calcium and the oxygen. Well, here's your ZDP, your zinc dithiiophosphate. That's your zinc and the phosphorus. Then you got some Mahle and some sulfur here, which are friction reducers, more calcium, and then a little more zinc down here again from another area. The key thing to understand about this is zinc isn't just an anti-wear additive. We know it's important for flat tappet cams and things like that, but it's also an antioxidant. So it's helping resist the thermal breakdown of the oil. And what can happen sometimes, an engine can be running okay and having no wear problem necessarily, but it's running at a high temperature, which is consuming the antioxidants. Then when it's all consumed as an antioxidant, now there's no ZDP left for wear protection. So what can happen, an engine running fine, then all of a sudden there's this huge wear problem that seems to come out of nowhere. Well, more than likely, it was the consumption of the additive package. Yeah. In fact, in used oil analysis, that's one of the things we recommend to do is, look at the new oil first. Compare the additive levels to your used oil. Because what you'll see sometimes is, before there's a problem, you'll actually see the additive levels beginning to deplete. It's consuming the additive package while it's running, and that normally precedes that increase in wear metals.
Interesting. So basically, if you catch it before, you go from a little bit of wear on the bearings to finally, as we had some of the other bearings, where it just finally is
gone. Yeah,
it's gone, and you're getting substrate eventually to the bearing that spun and failed, and could have been prevented by just changing your oil.
Well, the name alone says it. Additives are something that are added to the oil. It's there to help assist the base oil do its job. When they're depleted and gone, the base oil is by itself, and if the conditions are pretty harsh, guess what? It's not going to last very long, and if oil doesn't last very long, your engine's not going to last very long.
Exactly.
Okay, so we went through all of these things of how you can kind of utilize listening to the engine, because it's going to tell you a story.
It's telling you a story, yeah.
And we just talked about it. The oil will actually tell you a story as well. So between the engine speaking and the oil talking to you, you can learn a lot about how to catch a failure before it becomes catastrophic. But you also happen to have your own example of a catastrophic failure that's quite spectacular. We couldn't let you get away without seeing how spectacular this is. So, Dan, tell them the story.
So sometimes reports tell a story, you don't like what they're saying.
No, all stories are fine.
This was one of those cases. So I'm a family man, and I scheduled this family vacation. We went to the mountains, and I got my truck, and we hauled the camper, and we're going to the mountains, camp for the week. But before that, being the great father I am, I brought my truck to the dealership to change oil.
Smart move, man. Good.
Exactly.
Be proactive.
I know, the dealership. So little did I know, the relief valve on the filter was not in there.
Uh-oh.
So as I was going down the road, vacation went great, came back down the interstate, and all of a sudden, boom, things went bad. I've looked at thousands of bearings in my life.
Right.
And I officially...
A lot of bad ones, too.
Yep. I officially own the worst bearings I've ever seen came out of mine. So...
Let's show them.
So as time went on, we rebuilt the engine. So...
Now, apparently you said earlier, this is not a thrust bearing?
Nor was this a thrust bearing. So...
This is spectacular, Dan. So this is the result of a filter not filtering.
That is correct. So it went in bypass mode as soon as they changed the oil because the relief valve was not in there.
Right.
So this can happen if you use a cheap filter with poor filtration, relief valve not in there, and it's consumed so much debris that it finally just totally destroyed the bearings to the point of, obviously, an engine failure.
Yeah, filters are really important. Clean oil.
Clean oil is your
best friend. Back to that first slide, right? Contamination, the number one cause of failure. Yeah, I guess you have the living proof of that.
I do, and it was very costly for me, and great family memories, not in a good way, but they're memories.
Well, hopefully your lesson can be a lesson to everybody else on how to prevent bearing failures in the future. Hope you enjoyed the segment. Thanks for watching.
Thank you.
What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.